Partial fraction decomposition is a way to break a single fraction up into smaller fractions as long as its denominator will factor. The idea, if you look at something like, let's do 7/15. Since 15 we know has factors of 3 and 5, this means technically this could have been created by adding two fractions together that were thirds and fifths to get a common denominator of 15. The question here would be, well, what did those things on top need to be to give us those numbers? Well, that's what we're going to take a look at today with this, except for instead of just being numbers, it's going to be polynomials. So let's say if we had a fraction like 6 over x squared plus x minus 12. Well, since the denominator will factor, and that'll factor what, x plus 4x minus 3, and the idea is exactly the same. That means that this could have been the common denominator when we added two fractions together that had these two factors as their denominator. So since these are linear distinct factors, each one can just go on the bottom. Now, how do you know what goes on the top? Because we have polynomials involved here this time. Well, it's always going to be the generic polynomial 1 degree less than what's being represented in the denominator. Since this denominator is a linear term, that means on top is 1 degree less than linear, which is a constant, so we would just put something like a up there. Again, since this is a linear, or was a linear factor, then we're going to put a polynomial 1 degree less than that on top, which would be something like b. All right, once you do that, you need to solve for all the constants that we have here. So you always here, clear your fractions by multiplying through by your least common denominator, minus 3, x plus 4. Now from this stage, there's two different ways to approach this. I'm going to kind of show you both ways here, and sometimes you have to do a combination of both. The first thing is this has to be true no matter what the value of x is. So we've got to find the a and b that makes this true for all values of x. So if it's got to be true for all values of x, you can pick any x value you want. So you can do something like, let's let x be equal to 3. Now you can see why I would do that, because it would make this whole piece go away and be very easy to figure out what b is. So if x is equal to 3, you'd end up with something like 7b. So now we have a value for b. That's not 7/6, 6/7. Now we could also let x be another value. Let's let it be -4 to get rid of that. So if x put -4 into there, we'd have 6 is equal to -7a. So a is equal to -6/7. So now we have a value for a and b. So technically we can go back up here and say our original fraction was -6/7 over x plus 4 plus 6/7 over x minus 3. So we were able to break the original fraction up into two pieces. Now this is one way to do it, and when you have distinct linear factors, this is the easiest way to do it. However, sometimes you may have to equate coefficients. So I'm going to do the same thing again, but I'm going to bring this up here to the top to show you another method that you may have to use. Bx plus 4. All right. Go ahead and distribute everything else. So that's ax minus 3a, bx plus 4b. And then group by powers of x. So here we have some x's. So I have a plus bx, if you factor that out. And then your constant is -3a plus 4b. All right, so I grouped by powers of x. Now equate coefficients. Let's see, on this side, this is the coefficient in front of the x. The coefficient in front of x on this side, well, since I don't have any x term, that means that a plus b would have to be 0. Whatever the constant is on this side has to be the constant on this side. So I know -3a plus 4b would have to be equal to 6. So it's a system of equations. Solve the system any method that you know. So I'm going to use the substitution method here. We can see that a is equal to -b. Plug that in over there. So that's excuse me, b plus 4b is equal to 6. 3b plus 4b is equal to 6. 7b is 6, or b is 6/7. Since b is -6/7, and I know a is equal to -b, A is equal to negative 6/7. Okay, so you can see we ended up with the exact same answer. Of course, this was much quicker because the terms were very easy to deal with. The more complicated these denominators get, the more likely you're going to have to do a system of equations. So let's take a look at another example to where the denominator is more complicated and what we're going to have to do with it. So let's say we have 2x over, let's do, I don't know, x minus, I'm going to go ahead and factor this, x minus 4 squared. All right, I'm going to change this just a little bit. Okay, so a much more complicated denominator. We have x squared minus 3 times x plus 4 quantity squared. So if you think about how we would break this up, x squared minus 3, x plus 4 squared. Well, we have a couple of different things going on here. First, we have a quadratic term. So above this, we would put a term 1 degree less, which would be linear. A generic linear term would be something like ax plus b plus. Now, anytime you have a repeated term, in fact, you know what I'm going to do? Whatever. So anytime you have a repeated term, what you need to do is represent that as many times as it is repeated. Since that's repeated twice, I'm going to end up with 2 terms for this. What you do is you take whatever's being repeated and raise it to all the powers up to what the power's repeated. So since it's repeated twice, I'm going to do x plus 4 to the first and then x plus 4 squared. If this was a cube, then I'd have plus x plus 4 to the third, so on and so forth. Now what goes on top of these guys? Well, on top of these guys is going to be 1 degree less than what's repeated. Now here this is a linear term being repeated, so a constant goes on the top of that. I've already used A and B, so let's use C. Now the big mistake we see here is you're like, oh, that's quadratic. No, it's not, because we represented its repeated terms. So since we've done that, we just represent whatever's being repeated on the top. So we put something like D here. All right, now you'd follow the exact same thing. Now this one's going to be a lot harder because we have a lot more variables. Multiply through by your least common denominator, which is always the denominator on this side. And then you can pick values for x and or come up with a system of equations. So let me give you one of these to try to see if you can represent it broken apart. So let's say I gave you about 7x over x to the third x minus 3 x minus 4 squared. All right, there's going to be a ton of pieces here. That's going to go almost all the way across here. So do me a favor, hit pause and see if you can expand that out into all the pieces. All right, let's take a look at here. If you're back, which you are if you're hearing me, so x minus 4 squared. All right, so the x cubed, that's being repeated 3 times. So I'm going to have an x squared, and an x cubed. Since the x is what's being repeated, that's linear. Above that goes a constant. All right, the x minus 3 just is a linear term that occurs 1 time. So all I need is a constant above that. The x minus 4 is a repeated factor, so we have to repeat it all the way up to the highest power. Again, since it's a linear term, a constant goes on the top of those. All right, there you go. You clear your fractions, solve for A, B, C, D, F. You probably want to use a computer for something this long and messy. Make sure that you can do this because it's going to be extremely useful in the rest of this chapter.